Select the major product of the following reaction sequence. So if we take a look at what we are starting with here, we have this simple secondary alcohol. So we have a secondary alcohol. And the first thing we're doing is we're treating this with PCC and methylene chloride. So PCC is pyridinium chlorochromate. So this is a selective oxidizing agent that will take, so PCC would take a primary alcohol and form an aldehyde. And if it's a secondary alcohol, secondary alcohols are just oxidized to ketones regardless of your oxidizing agent. So where this is a secondary alcohol, we're going to form a ketone when we react this with PCC and methylene chloride. So a lot of times we associate PCC with making aldehydes, but you can only make an aldehyde if your starting material is the primary alcohol. So we're going to make this ketone. And what we're reacting this ketone with is an ylide. So this is your reagent for the Wittig reaction. And so we can draw a resonance structure of that ylide if we want, that puts the lone pair of electrons onto the carbon. And that might be handy for us to draw a mechanism, because then we can see that this carbon atom is going to be nucleophilic. So let's go ahead and draw that. So if we put that lone pair of electrons on that carbon also has a hydrogen. That would be the third bond that is not shown in the skeletal structure. And then it also has these two carbon atoms, this ethyl group. So CH2, CH3. All right, and if we've put that on there, we got a negative charge, and that has taken electrons away from the phosphorus, so the phosphorus would have a positive charge, as well as those three phenyl groups. And so what I'm setting this up for here is for the Wittig reaction. So let's label that this is a Wittig reaction. And so what's going to happen here is a really interesting mechanism. So your nucleophilic carbon is going to attack the carbonyl, which is not too surprising. But then this pi bond is going to swing around and attack that phosphorus. Because phosphorus-oxygen bonds are very strong bonds, and that is the driving force of this whole reaction. And so we're going to form this four-membered ring intermediate. So here's our four-membered ring. So we've got the single bond between the carbon and the oxygen, and then we've got a bond to this carbon. We'll put a hydrogen on there, as well as its ethyl group, a bond to the phosphorus, and then we have this oxygen-phosphorus bond. And so you get this four-membered ring intermediate, which quickly collapses. And it collapses to form the alkene and the phosphorus-oxygen double bond. And so I like to draw my arrow going to form the phosphorus-oxygen double bond first, because I think of forming that strong bond as what's driving this reaction. So to form that phosphorus-oxygen double bond, and then these electrons are going to come in to form an alkene here. So what we're going to be left with then is our six-membered ring. So we're going to have a double bond to this carbon, which has a hydrogen, as well as that CH2CH3. And we have also formed the triphenylphosphine oxide. That is a byproduct, and it is often left out when you're looking for the major product. This would be something that you would have to separate from your product and throw into the waste container. And so we drew the mechanism here. If you want a short way of doing it, you will notice that the carbon atom of your nucleophilic carbon of your ylide essentially snaps in place where that oxygen was with a double bond, right? So we can see these 1, 2, 3 carbon atoms replacing that oxygen 1, 2, 3. And we can see that that matches up with our option B.